Hello everybody, and welcome to our video on evaluating limits algebraically and continuity. So continuity is one of the most powerful tools we have to evaluate limits algebraically, and it saves us a whole lot of trouble. So let's take a look at the definition of continuity, because that definition is going to be our trick, so to speak, for how to evaluate these things. So when we take a look at this definition, it says that we say that a function f of x is continuous at c if the limit as x approaches c of f of x equals f of c. So if we take a look at this graph, right, we've got c here, this is a point on the graph, and the corresponding y value is f of c. Well, let's try to fix that pen mark there. There we go. So if we take a look, what is the graph approaching from the left and right? Well, it's approaching this value f of c. In other words, the value of the limit is the same as the dot on the graph. So that's exactly what we expect continuity to describe, right? It describes something where the value being approached from both sides is the value of the function. So alternatively, let's draw a couple quick graphs here. If I have a limit that breaks in the middle. So here, this is not continuous, and we know that from our intuitive understanding. So we think back to like algebra courses, we would describe continuity as there's no breaks in it, no skips, no jumps, no holes. So intuitively, this matches up exactly to what we have here, because if we have a break in the graph, that means that the limit doesn't exist. And if the limit doesn't exist, it certainly can't be equal to the value of the function. Similarly, if we have a hole in the graph, this is not continuous, it's got a hole in it. So here, the limit does not exist. And here, f of c is undefined. Well, if there's no value for f of c, then certainly it can't be equal to the value of the limit. And similarly, maybe the limit exists, and maybe the function is defined, but maybe the value for f of c is up here. So the value of the limit is not equal to f of c, and so we would also say this is not continuous. But in this case, it's not continuous because the values are not equal. But those are all of these conditions are built into the definition. If the limit doesn't exist, they can't be equal. If f of c is undefined, they can't be equal. And if f of c isn't equal to the value of the limit, then obviously the definition isn't satisfied. So that's the first big tool. In other words, if we know that a function is continuous, so this is why this tool is so useful to us. If we already know a function is continuous, you can evaluate the limit by just plugging in the number. That's what this says. If the function is continuous, then by definition, evaluating the limit is the same as plugging the number into the function. So we can't make it any more simple than that. Now, of course, not all functions are continuous, and that's why we have this theorem right here. That's our second major tool for evaluating finite limits algebraically. If f of x equals g of x for all x except x equal to c, then the limit as x approaches c of f of x equals the limit as x approaches c of g of x. So in other words, what this says is you've got two functions, and these functions are basically the same everywhere, except maybe one of them, we'll call this one f, has a discontinuity. And let's say the other function, we'll do that one in, how about green. So maybe this second function is the same, travels the same path, but it's continuous. Now, the theorem doesn't require continuity of either of the functions. It's not a requirement for the theorem to be true, but this is how we typically use it. We've got two functions, one that's not continuous, and this g function that is continuous, but they're the same everywhere else. Maybe g takes this value up here, whereas f has a whole, or sorry, f takes that value up there, where its hole is, but g is continuous and passes right through that hole. Well, both of those functions still approach the same value. So that's all this theorem says. These two functions are equal everywhere except at the single point. Well, the limit doesn't care about the single point. The limit cares what's happening on either side. So these two things have the same limit. All right. Now let's go ahead and start approaching this. So one thing that we have to keep in mind is functions that we know are continuous. Now, how do we actually show that these functions are continuous? We actually use the rigorous definition of the limit, but we replace L with f of the value, f of c, whatever c is here. And that's a little complex in general to do for this course, so we're just going to use these results that we've proved in analysis. So we know that all of the following functions are continuous on their domains: polynomials, trigonometric functions, rational functions, exponential functions, and logarithmic functions. Now I want to be clear here. On their domains is the important part. All of these functions are continuous wherever they are defined. Not all trigonometric functions are defined everywhere. Tangent of x is undefined at pi over 2, for example, and many other places, right? So many of these functions have places where they are undefined. Square roots are not defined for negative numbers. Logarithmic functions are defined only for strictly positive numbers. So we have to keep in mind the domains of the functions, but as long as you know their domains, anywhere, anytime you're in the domain, you're fine. They're continuous. So let's go ahead and start solving some problems. This is a polynomial. Polynomials are continuous. So I can just apply continuity here, and I'm going to note what I'm doing. Apply continuity. And that tells me that since this is continuous, I can just plug in -1 in place of x, and I will have evaluated my limit. -1 squared is 1, minus 8 minus 3. That's 1 minus 11, that's -10. And let's move on to the next one. Okay, so here is an important idea, which is that the sums and differences of continuous functions are continuous themselves. So we look here, e to the x minus sine of pi x plus x to the 5th. All of these are continuous functions. Their domains are all real numbers, so we don't have to worry about where x is. So we can just evaluate. Use continuity. Continuity says the limit is what you get when you plug in the number. Sine of 2 pi is 0, and 2 to the 5th is 2, 4, 8, 16, 32. This is plus 32. All right, that's it for that one. Moving on. Okay, now this one's trickier because this is a rational function, and this function, when I plug in x equals 2, this is undefined. You get a 0 in the denominator. So this is not continuous at 2. So what we're going to do is first factor this thing. And now what do we see? We've got this x minus 2 divided by x minus 2. Now this is undefined when x is equal to 2, but otherwise they would be equal to 1. X minus 2 over x minus 2 is 1. And remember, when we talk about limits, right, when we talk about that evaluation theorem, this evaluation equivalence of limits theorem says, hey, as long as they're equal everywhere except at c, then their limits are the same. So that tells us that when we apply this theorem, that it's the same limit when I cancel those factors as the limit of x plus 2. And now we have a linear function. That's a continuous function. So I can plug in using continuity. 2 plus 2 is 4. So two major tools here, right? We can cancel discontinuities, and that canceling will give me a limit that's still the same as long as nothing else about the function is changing. And then I can use continuity to evaluate this thing. Okay, so let's move on to another example. So again, I see if I plug in 3 into the denominator, I get 9 minus 3 minus 6. That's 0. So I would be dividing by 0. So this thing is undefined and not continuous there. So what I'm going to try to do again is see if I can factor the top and bottom and see if I can get rid of that discontinuity. So up top, we need factors of 3 that add up to negative 4. So that would be x minus 1 and x minus 3. And in the denominator, we need factors of negative 6 that add up to negative 1. So that would be x minus 3 and x plus 2. And so we can cancel x minus 3 divided by itself because that would equal 1, at least everywhere except for x equal to 3. And so the theorem tells us that this is the same as the limit as x approaches 3 of x minus 1 over x plus 2. And all we need is continuity at 3. So this function is still not continuous at negative 2, but we don't really care because we're only looking at the place where we're taking the limit. I don't get 0 in the denominator anymore. So this thing is continuous at that point, and I can just plug in 3 minus 1 over 3 plus 2 is 2 over 5. All right, let's tackle another one. We're just going to burn through these in no time. Evaluate the limit as x goes to 0 of tangent of x divided by sine of x. So if I plug in 0 in the denominator, I get sine of 0 is 0. I can't divide by 0. This thing is not continuous here. So I'm going to try using one of my trigonometric identities. Tangent of x equals sine of x over cosine of x. Okay, well that seems useful. Now let's rewrite this division as multiplication by the reciprocal. So sine of x over cosine of x times 1 over sine of x. And now it's a little easier to see that I can cancel sine of x over sine of x. You might have recognized that immediately, but I think it's a little clearer in this form. And so our theorem tells us that, hey, this is going to be the same as the limit when x approaches 0 of 1 over cosine of x. Now cosine of 0 is 1, so I don't have any discontinuity problems at 0 here. So I can just plug in 1 over cosine of 0, which is 1 over 1, which is 1. All right, let's continue. All right, now this one's a bit trickier. We've got the limit as x goes to 0 of x minus 2 cubed plus 8 over x. Now, you could multiply this out the long way. So first of all, what I'd like to do, if I could, I'd factor, but I can't factor here because I've got this x minus 2 trapped in this cube. So there's no factoring I can do to cancel my discontinuity with x equal to 0. So I need to multiply this stuff out first and see if there's something else I can do algebraically. Now you could use the long approach of x minus 2 times x minus 2 times x minus 2. Multiply this pair, take that result, multiply this. This is pretty long. Now, I'm not going to go into super big detail here, but if you're not familiar with using Pascal's triangle and the binomial theorem for multiplication of binomials, it's something that I suggest that you look up because it can save you a lot of time on this multiplication. So I'm going to kind of go through it quickly. You are welcome to do this the long way if you feel comfortable, but I'm going to demonstrate Pascal's triangle. So Pascal's triangle, the edge rows are diagonals are always 1s, and each row corresponds to a value n equals 0, n equals 1, n equals 2, n equals 3. And since we're cubed, I stop at n equals 3. Now, once I have 2, I get the term between them and below them by adding them together. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. So this is my Pascal's triangle up to n equals 3. And so when we have the expression x minus 2 cubed, these are my coefficients for my multiplication. If I write 1 times x cubed plus 3 times x squared times negative 2 to the first power plus, let me move that down a little bit so I have more space. plus 3 times x to the first power times negative 2 squared, plus 1 times x to the 0 power, so I don't need to write that, times negative 2 to the third. So see, all that happens is your first term is this coefficient times x to the power, and then your second term, you decrease the power of x, you increase the power of negative 2, and you go down the line like that. And these are your coefficients for each term. So this lets you skip all that multiplication and makes the simplification a lot easier. 3 times negative 2 is negative 6. Negative 2 squared is 4 times 3 is 12. And then that's negative 8. Again, if you're not quite comfortable with that or familiar, I suggest that you look up some problems with that, because they'll save you a lot of time on this sort of binomial multiplication. But you can always defer back to just multiplying it out the long way. Okay, so with that, let's go ahead and start evaluating this limit. This becomes the limit as x goes to 0 of x cubed minus 6x squared plus 12x minus 8 plus 8 over x. There's nothing applying to the parentheses here, so I can just drop those parentheses. But yeah, so we'll just do that. So we'll drop the parentheses, and when I drop the parentheses and I take the negative 8 plus 8, those cancel. I get x cubed minus 6x squared plus 12x minus 8 divided by, oh, not minus 8, minus 8 plus 8 cancels. Let's try that again, divided by x. Now up top, I'm going to factor the x out. And now I can cancel the x's. And so I get that this is going to be equal to the limit as x goes to 0 of x squared minus 6x plus 12. And my theorem tells me, hey, it's okay to cancel. Now this is a polynomial, and polynomials are continuous everywhere. So I can just plug in 0 squared minus 6 times 0 plus 12 equals 12. So to recap, I just want to reinforce this idea. Our goal here, evaluating these things algebraically, for the vast majority of problems is, if the function's continuous, just plug in, and if it's not continuous, find a way algebraically to get an equivalent function that is continuous. So the function only differs at the point where the discontinuity is. Okay, so now we've got one more of these. Well, I say one more, but not strictly one more, just one more on this page. Evaluate the limit as x goes to 3 of the square root of 4x minus 3 over x minus 3. So here, I can't factor because this stuff is trapped in the square root, and even if I did, I wouldn't see a factor of x minus 3. But my discontinuity happens when x is 3, I get 0 in the denominator. So you can kind of think of this square root like a prison. It's trapping these terms inside, and maybe if we could get rid of the square root, maybe we would have something where we could factor and cancel. So how do I get rid of the square root? Well, I use conjugates, which are the factors of difference of squares. A minus b times a plus b. Whenever you multiply a minus b and a plus b, you get a squared minus b squared. All right? So when we multiply by a conjugate, that will ensure that we don't have any square roots left in the expression, because each term will be squared and there will be no other terms. So that's why I choose to multiply the top by 4x plus 3 plus 3. But if I multiply the top by that, I have to multiply the denominator as well, so that I don't change the value of the function. Because here I'm effectively multiplying by 1. A number divided by itself, that's just multiplying by 1. Okay, so let's go ahead and start rewriting this limit. The square root times itself cancels the square root. In other words, that's a squared, a being the square root of 4x minus 3. So I just get 4x minus 3 minus b squared. So minus 3 squared, which is 9. Now, a really common mistake that I see on this particular type of problem is that students will try to multiply out the denominator. But remember, your goal is to cancel this thing. And if we multiply out the denominator, then we would have to refactor in order to be able to cancel it. So you'd actually be redoing some work and maybe causing yourself confusion in the process. So don't multiply out your denominator in these problems. It will mess you up. So we'll do a little bit of rewriting algebraically. 4x minus 3 minus 9 is 4x minus 12. And let's factor a 4 up top, and that gives us 4 times x minus 3 divided by x minus 3 times this expression with the square root here, 4x plus square root of 4x plus 3 plus 3. And now I can cancel. So my theorem tells me that this thing is equal to the limit as x approaches 3 of 4 divided by this thing plus 3. So now, as long as whatever's in the square root is positive and I don't get 0 in the denominator, this thing is continuous. So let's check. Well, when I plug in 3, I get 4 times 3 is 12 plus 3. That's the square root of 15 plus 3. So oh, wait a second. There's a plus there that should not have been there. I didn't let it affect most of my work, but that's not right. That should be 4x minus 3 plus 3. The switch should only occur here because my a term is the square root of 4x minus 3. Okay, let's see. Gotta be careful with those pluses and minuses. It's real easy to write something down wrong. But thankfully, when I actually multiplied them together, I wrote the correct thing, so it didn't affect any of my critical work. Just means I had to adjust that slightly. Okay, so now let's try that again. Now when I plug in 3, I get the square root of 12 minus 9, which is 9, that's fine. And I don't get 0 in the denominator. So this is 4 divided by the square root of 9 plus 3. Square root of 9 is 3, so that's 4 over 6, which is 2/3. Okay, there we go, one more down. Let's go ahead and move on. Okay, so now we've got a very important theorem. So remember I said like 90% of the time when we are evaluating limits that are finite limits, we're going to use this approach, the definition of continuity, and, somehow canceling the discontinuity. And that's what we did for all those examples, but sometimes we don't have that option. And the squeeze theorem is one of those tools that lets us deal with functions that are a little more complex. So the squeeze theorem says if f of x is less than or equal to g of x, which is less than or equal to h of x for all x, and the limit as x approaches c of f of x and the limit as x approaches c of h of x are both equal to L, then the limit of g of x is also equal to L. So g of x is this middle function. So before we go into the proof of this, we'll look at a picture. So we'll draw a quick picture here. This will be our c. And so we've got 3 functions. We've got a smallest function and a largest function, but all of them approach the same limit L at c. So we'll draw the smallest function in orange here. So this will be f. So that's just a function, still approaches the same L. And we'll draw our biggest function h in green here. So maybe that looks like that. And then g could do a bunch of stuff as long as g of x is in between these two functions the whole time. So this says that if g is in between these two functions, then it must get funneled into the same limit at that point. That's all this says. If you've got these two functions on top and bottom that approach the same limit, and you've got something between them, as that function moves towards c, it's got to somehow get funneled to that same y value, since it has to stay between the other two functions the whole time. That's all the squeeze theorem says. Okay, so let's take a look at the proof. So we use the epsilon definition of the limit for the proof here. So since we're given that f is less than or equal to g is less than or equal to h, then if I subtract L from each of these terms, the inequality will stay the same. And so if x is sufficiently close to c, we know that the f of x minus L will be between epsilon and negative epsilon. That's the definition of that limit existing. And h of x minus L will be between negative epsilon and epsilon. And so that means that g of x minus L, which was between those two things, is also between epsilon and negative epsilon. So g of x minus L is between negative epsilon and epsilon, which is the same thing as saying the absolute value of g of x minus L is less than epsilon, right? So that implies that the limit of g of x is L. Okay, so let's use it. So how do we use the squeeze theorem? Well, to use the squeeze theorem, we have to rely on properties of functions we know. So when I look here at this function, it's asking, evaluate the limit as x approaches 0 of x cubed plus 7x times sine of pi over x. But this expression, sine of pi over x, is undefined when x approaches 0, right? Or when x is 0, right? It's not going to be continuous because we can't divide by 0. But what I do know is that sine of pi over x, it doesn't matter what the input is, sine itself is the y value on the unit circle, so it has to be between 1 and negative 1 by definition, right? So if sine of pi over x is between negative 1 and 1, then x cubed plus 7x times sine of pi over x has to be between x cubed plus 7x and the negative of x cubed plus 7x. So if I take the limits of each of these expressions on the left, so the limit as x goes to 0 of negative x cubed plus 7x, well, that's a polynomial, so it's continuous. I can just plug in 0 and I get 0. And the same is true for the limit of this function on the right. Those limits are both 0, and that implies that the limit as x goes to 0 of my middle function here is also 0. And whenever we apply the squeeze theorem, we should cite it to make sure that whoever's reading our work knows we understood what we were doing and what we were applying. Okay, so yeah, that's it. That's the whole thing. So whenever you're trying to apply the squeeze theorem, you have to know the properties of your functions and use that to determine some similar related functions that can be an upper and lower bound for that function. All right, let's move on. So this is a slightly different type of problem. Evaluate the limit as x goes to 0 of the absolute value of x. So when we talk about the absolute value of x, again, we've talked about absolute value a few ways. We say, oh, it's the positive number, or it's the distance from the origin. Those are completely equivalent statements. But when we talk about the function, the absolute value of x, we typically need to define it in another equivalent, but slightly different way, to give us easier tools to work with for that. So the definition of the absolute value of x is x if x is a positive number or 0, and negative x if x is a negative number. So that might seem a little weird at first, but remember, if x is already negative, then multiplying by negative will make it positive. So if I have negative 2, that's negative 2, which is 2. But if I have the absolute value of 0, I can just say that's 0. Or the absolute value of 3, I can just say that's 3. Right, so this is the definition of the absolute value of x. So if I want to evaluate this limit, what I'll do is, since this is a piecewise function, I really need to evaluate this limit from each side of 0. So the limit of the absolute value of x as x approaches 0 from the right means values bigger than 0. So when I'm looking at values bigger than 0, I don't need the absolute value. I can just say x. That's a continuous function. That gives me 0. And then when I look at the limit as x approaches 0 from the left, well, that's numbers less than 0. So here I get negative x for my function. Again, still continuous. I can plug in 0. I get 0. These two things are equal. And when the left and right hand limits are equal, that's the value of the limit of our function. Okay, we're making pretty good progress so far. Let's go ahead and tackle another common issue. So far we've only been dealing in this section with limits that exist, but not all limits exist, as we know. So how can we determine algebraically that a limit doesn't exist? Well, one of the tools we have is that if we have a rational function, not a proper rational, but just a function divided by another function, and the limit of our top function is some non-zero number, and the limit of our bottom function is 0, then we can conclude immediately that the limit of their ratio does not exist, right? This quotient limit will not exist, because obviously we can't divide by 0. Now, you may say, well, a bunch of these things had zeros in the denominators before, but let's go ahead and scroll back up. So something we kind of blew off a little bit up here, which is that, hey, when we look here, x equals 2 gives me 0 in the numerator as well. And that's not what I'm talking about. All right, so again, all of these cases, you had, if you plugged in x equals 3, you got 0 in the numerator as well. X equals 0 gave you 0 in the numerator. So in these problems, we got 0 in the numerator and the denominator, both. So what this is stating is, hey, if you get 0 in the denominator but not in the numerator, that limit doesn't exist. And it should make kind of sense here, because the only reason we could evaluate these limits is because since they both had a factor that gave 0 in the numerator and denominator, that meant we were able to cancel those factors. If you only have a factor like that in the denominator, it can't be canceled, and you'll get a limit that doesn't exist. Now, on the other hand, if the limit as x approaches c of f of x is 0, and the limit as x approaches c of g of x equals 0, then the limit of their quotient is said to be of 0 over 0 indeterminate form. And this just means we got to try something else. That's why it's called indeterminate form. So the examples that we were looking at earlier were all indeterminate forms, right? So we just had to try some algebraic approach to solving them. But if we have that the numerator doesn't approach 0 and the denominator does, then we can just say, hey, that limit doesn't exist, and stop right there. Okay, so let's take a look at this example. If I take the limit as x goes to 2 of x plus 7, I get 9. And the limit as x goes to 2 of x squared minus 4, that's my denominator, that is 0. So the numerator doesn't approach 0, the denominator does. That implies that this limit does not exist. Done. Okay, now let's take a look at this one. Find the limit as x approaches negative 2 if it exists. So first I'll check and see if it's indeterminate form. Yeah, we weren't checking this in the earlier problems, but it's a good habit to get in, and you can usually check it mentally pretty quick. All right, so here I get 0 in the numerator, And when I approach -2 in the denominator, I get 0 for that as well. So this limit might exist. And this is the key thing with indeterminate forms. There's no guarantee that the limit exists. It's just possible. So we have to try some other approach to determine it, right? So in this case, our limit will be equal to the limit as x approaches -2 of x plus 2 over x plus 2 times x minus 2. Just factored my difference of squares. Canceled. This gives me the limit as x approaches -2 of 1 over x minus 2. So when I plug in -2, I get 1 over -2 minus 2. That's -1 over 4. All right, that's it for that one. So this is an indeterminate form, but we could try a different algebraic approach, and we're able to solve for the limit. Okay, example number 12 here. Determine if the piecewise function is continuous or not. So all we need for continuity, so the definition says that f of c equals the limit as x approaches c of f of x. So we have some useful facts that we can call on, which is that, so here, x squared plus 1, well, this is continuous for x less than 1. X squared plus 1 is continuous for all real numbers, but our function is only x squared plus 1 when x is less than or equal to 1. And on the border, we might have a problem. So, but everything less than 1, we get continuity. And likewise, -x plus 3, that's a line, so we'll get continuity for x greater than 1. But we have to worry about what happens at 1. So let's go ahead and evaluate f of 1. Well, that's simple enough. When x equals 1, I get x squared plus 1. So that's 1 squared plus 1 equals 2. Now for the limit, I need to evaluate the left and right hand limits separately. So we'll evaluate the limit from the left first. So since I'm to the left of 1, that's smaller than 1. So this is the same thing as the limit as x approaches 1 from the left of x squared plus 1. And when x approaches 1, I get 1 squared plus 1. That's 2. Now when I take the limit as x approaches 1 from the right, I've got negative, well, I should say of f of x. Now, since I'm approaching from bigger numbers than 1, I should be using this function. That's -1 plus 3, which is also 2. So these two things are equal, and that implies that the limit as x approaches 1 of f of x is 2, which is equal to f of 1, so the function is continuous. So again, we already knew that each individual portion of the function was continuous on the other sides, but the question was, do they meet at the same point? So essentially what this says is, like, when you look at the graph here and we go to x equals 1, it just says that both of these graphs approach the same, that's a negative slope. They approach the same point. They're continuous, they're not unbroken, or not broken, I should say. Okay, let's go ahead and move on. All right, let's determine if this piecewise function is continuous or not. So here, this time I'm going to just start with the limit and see what we get. So we'll deal with the limit first. The limit as x approaches 2 from the left of f of x. So again, we know that this is continuous for x less than 2, and we know that it's continuous for x greater than 2, right? These are both continuous functions, but what happens? Do the two pieces meet correctly? So when x approaches 2 from the left, I'm looking at this top function, x cubed, which is going to give me 2 cubed, which is 8. And when I look at the limit as x approaches 2 from the right, well, that means I'm going to look at this bottom function, x plus 4. That's going to give me 2 plus 4 is 6. Now, these two things are not equal, so the limit as x approaches 2 of f of x does not exist, and so f is not continuous at x equals 2. All right, that's it. Just apply the definition. All we're doing here is checking. Does f of 2 equal the limit as x approaches 2? And if the limit doesn't exist, it can't be equal to the function. All right, let's tackle this next theorem here. So this theorem is actually very hard to prove, but it's very easy to understand, in my opinion. The intermediate value theorem says, if f is a continuous function on the interval from a to b, and f of a is not equal to f of b, then for any value n between f of a and f of b, there exists a z in that interval between a and b, such that f of z equals n. So let's look at this in this picture here. It just says if you've got a function that's continuous, there's no broken gaps, there's no holes in it, and it's from a to b. Now, we haven't specified that a is smaller than b or vice versa, or that f of a is necessarily bigger than f of b. That's just the example for this picture. Nothing would really change here if you had a curve where f of b was bigger than f of a. It would be the same picture just turned around. So all this says is since it's unbroken, if I pick any number between f of b and f of a, any number, there's got to be some z between a and b that gives me that output on the function. When I plug in z, I get that in, because there's no gaps in the curve, right? So it's got to hit every value between f of a and f of b. That's all the intermediate value theorem says. So we can use the intermediate value theorem to justify a lot of things, and we're just going to look at one example here. Show that the equation e to the x equals x squared minus 1 has at least one solution. In order to do this, we have to actually be thinking about a function, not an equation, because the intermediate value theorem only tells us about the behavior of functions, but we can make that happen with just a little adjustment. So if we adjust our equation here, we get that e to the x minus x squared plus 1 is equal to 0. That's an equivalent equation, so we're going to consider the function f of x equal to e to the x minus x squared plus 1. And now I'm just going to pick some x values. Now I know which x values I'm going to pick, but if you don't and you're looking at a problem like this, you can just guess. And once you get a couple that work, that's good enough. You might have to guess a few numbers. That's totally fine. Usually you can kind of make educated guesses if you know your functions well, but guessing is totally fine until you find a couple that work. So I'm going to guess my first function, or my first value is going to be f of 0. So f of 0 is e to the 0 minus 0 squared plus 1. And I just picked that because I knew e to the 0 was easy to evaluate. That gave me 1 minus 0 plus 1, that's 2. So that's a positive number. Now I want to show that somewhere the function equals 0. That's what I'm trying to show here. So now I want a negative value. So I want to pick an x value that makes this small enough. And I know that e to the x gets smaller when x is negative because it becomes 1 over e to the x. And this square, I've got a negative in front of the square. So I'm going to just go with, let's say negative 2. See what we get. We get e to the negative second minus negative 2 squared plus 1. That's 1 over e squared minus 4 plus 1. That's 1 over e squared minus 3. And 1 over e squared is 1 over 2.7 squared. That's much smaller than 1. Minus 3, this is definitely a negative number. And so 0 is between 2 and 1 over e squared minus 3. So that implies that there is a z such that f of z equals 0. And obviously that z is the solution to this equation. So this theorem doesn't allow us to find the solution to this equation, but it does allow us to figure out a range. We know that the solution is going to be somewhere between the x values we picked, -2 and 0. So z is between -2 and 0. And we could potentially try more values out to narrow that solution down and approximate it. But again, it doesn't solve this the equation, but it lets us know if there are solutions. And an equation like this, where you'd have to use more complex approaches to finding those solutions, knowing that there are solutions is useful in and of itself. Okay, so last theorem we're going to touch on here. This should be a fairly quick one, the continuity and convergence theorem. If f of x is a continuous function and the limit as x approaches c of g of x equals k exists, then the limit as x approaches c of f of g of x equals f of the limit as x approaches c of g of x, which equals f of k. So that's that seems like a big complicated statement, but all this says is if I've got a limit of f of g of x, I can move the limit operator inside the function f. So we'll look at applying that in just a moment. But let's just take a look at the proof. The proof is pretty quick. Since f is continuous for any epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of g of x minus k is less than delta 1, we'll call it, then the absolute value of f of gx minus f of k is less than epsilon. So since g of x is the input to our function f, and k is the result of that limit g of x, we're thinking of these as our inputs to f, and that's why these are what we're bounding by delta 1. But since the limit as x approaches c of g of x is k, there's another delta greater than 0, such that when the absolute value of x minus c is less than delta 2, we have that g of x minus k is less than delta 1. So in other words, when the absolute value of x minus c is less than delta 2, the absolute value of g of x minus k will be less than delta 1, which gives us that the absolute value of f of g of x minus f of k is less than epsilon. And that gives us, by definition, that this limit as x approaches c of f of g of x is f of k. And k is this thing here. Okay, so you might want to pause that and look back at it and take a few minutes. But I'm going to go ahead and continue on. If you want to pause, go ahead and pause. We'll just go ahead and take a look at one example using this. So evaluate the limit as x approaches 1 of sine of x squared minus 1 over x minus 1 times pi over 6. So sine is a continuous function everywhere, and so when I use the continuity and convergence theorem, I just notate c apostrophe c, or you could do c ampersand, so c and c. I'm going to move that limit inside the function. As long as the limit of the thing inside exists, and we'll see that it does momentarily, all this theorem says is that I can move that limit inside. And now pi over 6, I can pull that out of the limit because it's a constant multiple. And we saw that in our limit laws from a previous section. So I pull that constant multiple pi over 6 out. And at the same time, I'm going to rewrite x squared minus 1 as x minus 1 times x plus 1. That's just my difference of squares. And so now we can start canceling. All right. Now, the definition of continuity tells me that I can just plug in 1 into this linear function, so I get 1 plus 1 is 2. So this is sine of pi over 3. And sine of pi over 3 is the square root of 3 over 2. Okay, that's everything I had for this section. I know this was a bit of a longer one than the last two, so thanks for sticking around. Have a great day. Bye.